There's a planet in our solar system that should not exist the way it does. Not because it violates physics in some dramatic science fiction sense. Not because it defies gravity or burns with impossible fire. It violates something quieter and more fundamental than that. It violates the logic of inheritance. It violates the expectation that a child should resemble its parent. It violates the idea that when something is born inside a spinning system, it should carry that spin forward, like a secret pass from one generation to the next, encoded in motion, preserved across billions of years. Every planet in our solar system inherited its rotation from the cloud of gas and dust that collapsed to form the sun and everything orbiting it. Every planet spins in the same general direction that cloud was turning. Every planet, that is, except one. Venus spins the wrong way. Not tilted, not wobbling off axis in some forgivable, explainable fashion. Reversed. Completely, stubbornly, inexplicably reversed. If you stood on the surface of Venus and watched the sky, the sun would rise in the west and set in the east. Your entire intuitive map of a day, of time, of how the heavens move would be inverted. And it gets stranger. Venus rotates so slowly that a single day on its surface, one full rotation, takes longer than an entire Venusian year. The planet completes a full orbit around the sun before it finishes turning around once. Day outlasts year. The calendar breaks down completely. 60 years ago, when radar telescopes first pierced Venus's permanent cloud cover and returned these numbers, the scientific community did not know what to do with them. They checked the measurements. They ran them again. They confirmed them through multiple independent instruments. The numbers were real. Venus was real. And Venus was doing something that no coherent theory of planetary formation had predicted. 60 years later, we still do not fully know why. This is not a story about a problem that science is close to solving and just hasn't announced yet. This is a story about a genuine, deep, unresolved mystery sitting in plain sight, 93 million miles from where you're sitting right now, spinning patiently in the wrong direction, waiting for us to figure out what happened to it. If you're new here, welcome. Get comfortable. Settle in, because this one takes time, and it earns that time. Subscribe if you want to follow along as we go deeper into the questions that don't have clean answers. Tonight, we're going to walk through everything that science currently knows and honestly admits it doesn't know about why our nearest planetary neighbor is behaving the way it is. We're going to start from the beginning. We're going to build up carefully, and we're going to end somewhere larger and stranger than where we started. That's a promise. To feel the weight of the Venus problem, you first have to understand how unremarkable Venus was supposed to be. When planetary scientists in the mid-20th century looked at the inner solar system, they saw a pattern. 4 rocky planets, each formed from the same general disk of material, each sitting at a different distance from the sun, each obeying the same basic set of rules. Mercury, close and battered. Earth, temperate and active. Mars, cold and geologically quieter than it once was. And Venus, sitting between Mercury and Earth, almost exactly the same size as our own world, almost exactly the same mass, almost exactly the same density and composition. The numbers are almost unsettling in how closely they match. Venus has roughly 81% of Earth's mass, which in planetary terms is essentially a rounding error. Its radius is about 95% of Earth's radius, meaning if you shrank our planet down by 5%, you would get Venus. Both worlds are rocky. Both are iron-cored. Both formed from the same inner zone of the same protoplanetary nebulae 4.5 billion years ago. If you were a chemist handed blind samples from early Venus and early Earth and told to say whether they came from the same source, you would say yes without much hesitation. This similarity is not coincidence. It is physics. Planets that form close together in a rotating disk inherit similar building materials because they're drawing from the same reservoir of dust, ice, and metal at similar distances from the central star. The disk composition varies with distance from the sun, but 2 planets sitting as close together as Earth and Venus, in astronomical terms, are pulling from essentially the same shelf. So the expectation was simple and well-founded. Venus should look like Earth. Venus should rotate like Earth, or at least in the same general direction, at a broadly similar speed. Venus should be a near-identical twin, perhaps a little warmer given its closer proximity to the Sun, perhaps slightly different in its surface geology, but fundamentally the same kind of world doing the same kinds of things in the same way. That expectation was not a guess. It was the prediction of angular momentum conservation, which is one of the most reliable and well-tested principles in all of physics. When a rotating cloud collapses into a disk and that disk fragments into planets, those planets inherit the rotational motion of the cloud. Every object in the forming solar system was embedded in the same turning frame. Every collision that built larger bodies from smaller ones happened within that rotating frame, so the angular momentum accumulated in roughly the same direction. The result should be a solar system where everything spins the same way, with small deviations caused by late collisions and gravitational tugs, but nothing fundamental. And yet, Venus turns clockwise. Viewed from above the solar system's north pole, looking down at the plane where the planets orbit, everything moves counterclockwise. The Sun turns counterclockwise. Earth, Mars, Jupiter, Saturn, Neptune, Mercury, they all rotate counterclockwise. The asteroid belt flows counterclockwise. The Kuiper belt flows counterclockwise. The entire solar system is a single enormous counterclockwise system. Venus is going the other way, and there is no small print that explains this away. This is not a subtle tilt. It is not a minor wobble. It is a full, unambiguous reversal. The planet rotates in the direction precisely opposite to its own orbit around the Sun, not slightly off, not mostly aligned with occasional retrograde tendencies. Opposite. The word for this in planetary science is retrograde, and it is not a word used lightly. Retrograde means something overwrote the default. Retrograde means something intervened. Retrograde means there is a story, and we don't know what it is. Let me give you the actual numbers, because reading them in sequence does something to your understanding that a summary cannot. Venus's sidereal rotation period, the time it takes to rotate once relative to the distant stars, is 243 Earth days. Venus's orbital period, the time it takes to complete one orbit around the Sun, is 224 Earth days. Stop and read those again. The rotation takes longer than the orbit. The day is longer than the year. If you lived on Venus, and you try to count your years by the number of days that had passed, you would complete an entire trip around the Sun before a single Venusian day had finished. The very relationship between day and year, which is so fundamental to how every civilization on Earth has organized time, agriculture, religion, and history, inverts completely on Venus. Your calendar would not just need adjustment. It would need to be rebuilt from an entirely different set of assumptions. Then there is the axial tilt. Earth's rotation axis is tilted at about 23.5 degrees relative to its orbital plane, and that tilt is why we have seasons, why the northern hemisphere gets more sunlight in June than December, why polar days and nights exist. It is a modest, comfortable tilt, and we have built our entire experience of the year around it. Venus has an axial tilt of approximately 177 degrees. 177 degrees is 3 degrees shy of being perfectly upside down. The North Pole of Venus, by the convention we use to define planetary poles, points almost directly opposite to where most planets' north poles point. The planet is, for almost all practical purposes, inverted. Now here is where physicists disagree on how to frame this, and the disagreement is not trivial. You can look at that 177-degree tilt and say, the planet has been flipped over, but its rotation relative to its own body is still in the original direction. The rotation hasn't reversed. The orientation has reversed. Or you can say, the tilt is essentially 0 degrees, the planet is upright, and it is simply spinning in the genuinely opposite direction. These two descriptions produce the same observable outcome. Geometrically, they are identical, but physically, they imply completely different histories, different forces, different catastrophes, or gradual processes. One story says Venus was turned upside down. The other says Venus gradually reversed its rotation. We cannot currently tell which story is true, and that uncertainty is, in a strange way, the heart of the entire problem. And then there is the speed, or rather the lack of it. Imagine standing on Earth's equator. You are, right now, moving at roughly 1,040 miles per hour because of Earth's rotation. You don't feel it. The atmosphere moves with you. Everything around you is being carried at the same speed. But the speed is real. Now stand on Venus's equator, hypothetically. The surface beneath your feet is moving at approximately 4 miles per hour. Walking speed, a brisk human stride. You could, in principle, walk fast enough to keep pace with the rotation of a planet roughly the size of Earth. That is how slowly Venus is turning. It is not a planet spinning. It is a planet barely moving, like a massive, silent top that is almost wound down, hovering on the edge of stillness. This is not just strange. It is deeply strange, and the strangeness compounds. Venus doesn't just spin wrong. It spins wrong, and it spins impossibly slowly, and its axis points almost exactly opposite to where it should. 3 separate violations of expectation, each one pointing in the same direction, which is towards something unusual having happened to this planet, something that left no obvious fingerprint, something that erased itself from the geological record before we could find it. To understand what makes Venus anomalous, you need to understand what normal looks like. And normal looks like a story that begins 4.5 billion years ago. The solar system did not begin as a collection of planets. It began as a cloud, an enormous, slowly rotating cloud of gas and dust, mostly hydrogen and helium, seeded with heavier elements forged inside previous generations of stars and scattered through the galaxy when those stars exploded. The cloud was cold and diffuse, and for a long time, it simply drifted, turning lazily in the galactic current. Then something perturbed it. A shock wave from a nearby supernova, perhaps, or an internal gravitational instability. The cloud began to collapse under its own weight. As it did, something subtle and important happened. A tiny initial rotation, the kind of gentle spin that any object in a universe full of moving things naturally picks up, got amplified. Angular momentum is conserved, which means when the cloud shrank, it had to turn faster to maintain its total rotational energy. The lazy drift became a genuine spin. The collapsing sphere flattened into a disk, the way pizza dough flattens when a skilled chef spins it in the air, centrifugal physics working at a cosmic scale. At the center, hydrogen compressed until fusion ignited and the sun switched on. Around it, the remaining material, a flat disk of gas and dust and ice and metal particles, began to clump. Dust grains collided and stuck together through static electricity and van der Waals forces. Clumps grew into pebbles, pebbles into boulders, boulders into kilometer-scale bodies called planetesimals. Planetesimals collided and merged into protoplanets the size of Mars or larger. And finally, those protoplanets swept up the remaining debris in their orbital neighborhoods and became the planets we know. Every step of this process happened inside the rotating frame of the disk. Every collision was between objects that were already orbiting in the same direction. Every merger produced a combined object that, on net, continued rotating in that same direction. This is why the fingerprint of the original cloud's rotation is preserved across almost the entire solar system today. It has been passed down through 4.5 billion years of collisions, each one reinforcing the same inherited spin direction. This is what the word prograde means. Prograde rotation is the default. It is what you get when the physics runs its course without extraordinary interference. Every planet in the solar system that rotates prograde is simply doing what the formation process wrote into it. The spin direction is a fossil, encoding the rotation of the original cloud, preserved in every planet that hasn't been disturbed. Retrograde is the opposite. Retrograde rotation doesn't happen by default. It requires an intervention. It requires something to have disrupted the inherited spin, to have come in from outside, or to have acted on the planet over time and rewritten what formation wrote. When astronomers encounter a retrograde object, they don't shrug. They look for the story. They look for the thing that did the rewriting. For moons, the story is usually capture. Triton, the largest moon of Neptune, orbits in the retrograde direction. The overwhelmingly favored explanation is that Triton didn't form around Neptune at all. It was a Kuiper belt object, a body of ice and rock from the outer solar system, that wandered too close to Neptune, lost enough energy through tidal interaction and gravitational drag, and got captured into orbit. It is moving against the grain because it came from somewhere else, from a different part of the solar system with different local conditions, and it brought its own rotational history with it. For planets, capture doesn't work. A planet the size of Venus, forming from inner solar system material, cannot simply drift in from elsewhere and settle into a circular orbit 93 million miles from the Sun. The orbital mechanics don't permit it. The composition doesn't support it. Venus formed where it sits, and yet Venus rotates retrograde, which means something happened to Venus after it formed. Something reached in and rewrote the fossil. The question is what? And the answer, 60 years later, is still, we are not entirely sure. For most of human history, Venus was a mystery for a simple and frustrating reason. You couldn't see it. Not because it was dim. Venus is actually the brightest object in the night sky after the moon. It is bright enough to cast faint shadows on a clear night. But the brightness comes entirely from its cloud cover, a permanent, total, unbroken deck of sulfuric acid clouds that wraps the planet in an opaque white shroud. Telescopes, no matter how powerful, showed astronomers nothing but a featureless cream-colored sphere. There were no surface features to track, no mountains or craters rotating across the disk to measure. Venus was optically a closed book, so people guessed. Before the radar era, estimates of Venus's rotation period varied enormously. Some astronomers believed Venus was tidally locked to the Sun, meaning one face always pointed toward the star, the same way the moon always shows Earth the same face. If that were true, a Venusian day would equal a Venusian year, which was strange but at least internally consistent. Others thought Venus rotated in roughly 24 hours, because why wouldn't it, being so similar to Earth in every other measurable way? The range of published estimates was wide enough to be embarrassing in retrospect. There was no consensus because there was no data. Venus was a guest dressed up in scholarly language. Then radar arrived. In the late 1950s and early 1960s, radio telescopes had advanced to the point where they could do something optical telescopes could not: bounce signals off Venus's surface and measure the returning echo. The technique works by exploiting the Doppler effect. When you send a radio pulse toward a rotating planet, different parts of the surface are moving toward you or away from you at different speeds. The limb rotating toward you returns the signal with a slightly higher frequency, like the approaching note of a passing train. The limb rotating away returns it at a slightly lower frequency. By analyzing the spread of frequencies in the returning signal with precision instruments, astronomers could extract the rotation rate directly without ever needing to see the surface. In 1961 and 1962, working with data from the Goldstone and Arecibo radio facilities, researchers began returning results. And the results were not what anyone had anticipated. Venus was rotating slowly, far more slowly than any prediction had suggested, much closer to tidally locked than to Earth-like. The sidereal period came out to approximately 243 Earth days. That alone was shocking. But then came the direction. Venus was rotating retrograde, backward, against the grain of everything else in the solar system. The measurements were checked. They were repeated. They were confirmed by independent groups using independent instruments. By the mid-1960s, the result was solid. Venus rotates opposite to its orbital motion, with a period of 243 days and an axial tilt of approximately 177 degrees. These were no longer hypotheses. They were facts, and the planetary science community had no framework to put them in. In 1965, researchers Goldstein and Carpenter published one of the early major discussions of this anomaly. The spirit of their conclusion, paraphrased carefully, was that the only real limit on explanations for Venus's rotation was the imagination of the theorists, which was the scientific community's polite way of admitting that nobody knew what had happened and that every proposed explanation was roughly as good and roughly as problematic as every other one. This is what a genuine paradigm disruption looks like. You have an observation that doesn't fit. The observation is solid, so you don't get to dismiss the observation. You have to go back and ask where the framework was wrong. You have to ask what assumption you were making that the universe has now contradicted. And you have to begin the long, uncomfortable process of building a better framework, one that can accommodate both what you already understood and what you now know. That process has been running for 60 years. It has produced several serious competing hypotheses, each with strengths, each with gaps, none of them decisive. We are still in it. Before we can evaluate any of the explanations, we need to sit for a moment with the actual physics of what it means to reverse a planet's rotation. Because the words are easy to say and surprisingly easy to underestimate. Spin is not just a property. Spin is a form of stored energy and stored momentum. The technical term is angular momentum, and angular momentum is one of the most rigorously conserved quantities in physics. To change the angular momentum of a system, you cannot wish it. You cannot slowly encourage it. You need an external torque, a rotational force applied from outside the system. Without external torque, whatever spin a body has, it keeps. This is why the figure skater analogy has survived so long in physics education. When a skater pulls her arms in while spinning, she does not add angular momentum. She conserves it while changing how her mass is distributed, which forces her rotation rate to increase. The angular momentum itself is untouched. It is locked in for a planet. This means that spin once set at formation is supposed to persist for an extraordinary length of time. A planet's orbit can be gradually nudged by gravitational interactions with other bodies. Its axis can precess slowly. Small perturbations accumulate, but the rotational period itself, and especially the direction of rotation, is extremely stable. It is a fossil in the most literal physical sense. It encodes the conditions of formation. Is supposed to remember. Venus's spin does not remember formation, or rather, it remembers something different, something no standard model predicted and nothing obvious explains. To reverse the rotation of an object with Venus's mass, you need to remove all of its existing angular momentum in the prograde direction and replace it with angular momentum in the retrograde direction. That is not one step. That is two enormous steps. First, you slow the planet to a stop, which requires extracting all of the spin energy it accumulated during formation. Then you spin it up in the opposite direction, which requires injecting a comparable amount of energy in the new direction. The numbers involved, when you actually calculate them, are staggering. We're talking about energy budgets that dwarf the output of nuclear reactions operating at geological timescales. There are fundamentally two ways this can happen, and they imply completely different histories. The first is a rapid catastrophic event. Something large strikes Venus or interacts with it violently, delivering an enormous amount of angular momentum in the retrograde direction very quickly. The event is brief. It is traumatic. It reshapes the planet in ways that should leave evidence. The second is a slow, sustained process. Something acts on Venus continuously over billions of years, gradually draining its prograde angular momentum and slowly building up retrograde angular momentum in its place. The process is quiet. It leaves no single dramatic scar, but it is patient in a way that only cosmic time allows. Both pathways, in principle, can produce Venus as we see it today. A dramatic impact could have flipped it. A slow tidal process could have reversed it. And this is the first hint of the fundamental problem that haunts this entire field. The same endpoint can be reached by multiple different routes, and we cannot tell from the endpoint alone which route was taken. Here is something that often gets left out of simplified explanations of Venus's rotation, and its absence leaves those explanations misleading. Venus's atmosphere is not a passive backdrop. It is an active participant in the planet's rotational physics. And once you understand what the atmosphere is actually doing, the problem becomes simultaneously richer and more difficult. Venus's atmosphere is massive, 93 times more massive than Earth's atmosphere. The surface pressure on Venus is approximately 92 times Earth's surface pressure, equivalent to the pressure you would experience nearly a kilometer beneath the surface of the ocean. The atmosphere is predominantly carbon dioxide, with a thick cloud deck of sulfuric acid droplets sitting around 65 kilometers altitude. The greenhouse effect is so extreme that the surface temperature hovers around 465 degrees Celsius, hot enough to melt lead, hotter than Mercury despite Venus being nearly twice as far from the Sun. But the most peculiar atmospheric feature, for the purposes of understanding rotation, is this. The upper atmosphere of Venus is rotating dramatically faster than the planet beneath it. The clouds at 65 kilometers altitude complete a full circuit of Venus in approximately 4 Earth days. The solid surface below them takes 243 Earth days to rotate once. The atmosphere is moving roughly 60 times faster than the planet. This phenomenon is called superrotation, and it is by itself one of the most genuinely mysterious behaviors in planetary atmospheric science. We can describe it. We can partially model it. We cannot yet fully explain why it exists with the magnitude it has. Why does this matter for the rotation story? Because the atmosphere contains real, significant angular momentum. A mass of gas 93 times Earth's atmosphere, moving 60 times faster than the surface, represents an enormous reservoir of rotational energy. And that reservoir is connected to the solid planet beneath it. The two exchange angular momentum continuously through surface friction and through something called thermal tides. Thermal tides are not ocean tides. They are oscillations in the atmosphere's density and pressure caused by solar heating. The day side of Venus gets heated by the sun, causing the atmosphere to expand and become less dense on that side. The night side is cooler and denser. Because the atmosphere is rotating and because the heating is continuous but not instantaneous in its effect, the actual density distribution lags behind the heating pattern. There's a slight offset between where the sun is and where the atmospheric bulge is. That offset creates a gravitational effect on the solid planet below, and that gravitational effect exerts a torque. This torque is not negligible over billions of years. It can be significant, and crucially, it pushes in a direction opposite to the gravitational tide exerted by the sun itself on Venus's solid body. The gravitational tide from the sun acts to slow Venus's rotation and push it towards synchronous lock, one face permanently toward the sun. The thermal tide from the atmosphere pushes back, resisting that lock, pushing the rotation in the retrograde direction. The two forces are in permanent tension, and their balance or imbalance over 4.5 billion years may be the entire story of why Venus rotates the way it does. This is the insight that fundamentally changed how scientists think about this problem in the early 21st century. Venus's rotation is not a property of solid body. It is a property of a coupled system, the solid planet and the massive atmosphere acting together, exchanging angular momentum through multiple mechanisms, both responding to external forces from the sun and from the rest of the solar system. Any model that treats Venus as a simple rigid ball spinning in space is going to miss the actual physics. And here's where the depth of the problem becomes almost intimidating. Because the atmospheric coupling has been changing over billions of years. The atmosphere of early Venus was not the atmosphere of Venus today. Early Venus may have had liquid water oceans. It may have had a thinner, less extreme atmosphere. Its greenhouse effect was certainly different. The coupling between atmosphere and planet, and therefore the torque the atmosphere was exerting on the rotation, was different then. The history of Venus's spin is entangled with the history of Venus's atmosphere, which is entangled with the history of Venus's water, which is entangled with the history of the early solar system. Every thread leads to every other thread. When the radar results came back in the early 1960s and the scientific community confronted Venus's retrograde rotation for the first time, the first reflex was the same reflex it usually is when a planet does something unexpected. Something must have hit it. It is easy to understand why. Impact is the most physically intuitive explanation for a dramatic anomaly. The solar system's history is saturated with impact events. the moon-forming collision that gave Earth its satellite, the impact that created the Calorus Basin on Mercury, the bombardment history written across the cratered face of the moon, the enormous impact basins of Mars. Large collisions between sizable bodies were common in the early solar system, particularly during the first few 100 million years while the protoplanetary disk was still clearing out. Proposing that Venus suffered a spin-altering impact was not proposing something exotic. It was proposing the most available physical mechanism. The specific version of the hypothesis that early researchers considered was a glancing blow from a large body, something on the order of Mars-sized or larger, hitting Venus obliquely after the planet had mostly finished forming. The geometry would be such that the impactor delivered angular momentum in the retrograde direction against Venus's initial prograde spin. If the impact was large enough and hit at the right angle, it could have first slowed Venus's rotation and then pushed it past zero into the retrograde regime. A cosmic cue ball striking at just the right angle. The energy calculation is straightforward to set up. You know Venus's current angular momentum. You estimate what it probably was at formation, similar to Earth's in both magnitude and direction. You calculate how much angular momentum needed to be delivered in the retrograde direction to reach the current state. Then you work backward to determine what size and speed impactor could deliver that angular momentum in a single collision. The answer you get is an impactor substantially larger than anything that hit Earth to produce the moon. It would have been one of the most energetic events in the inner solar system's history. And that is where the hypothesis begins to fracture. An impact that large doesn't just change a planet's spin. It reshapes the planet. An impactor with enough mass and velocity to reverse Venus's rotation would release energy on the order of 10 to the 32nd joules upon impact. That is enough energy to melt a significant fraction of Venus's mantle. It would blow enormous quantities of crustal material into space. It would, according to essentially all impact physics models, produce a debris disk around Venus, and that debris disk would over time coalesce into one or more moons. Venus has no moons, not a single one, 0. This is in its own right one of the most remarkable facts about our neighboring planet. Earth has the moon. Mars is Phobos and Deimos, small but real. Even the giant planets have enormous moon systems encoding the history of their formation. Venus orbits alone, with no companion, no satellite, nothing in orbit at all. If a Mars-sized body struck Venus and reversed its rotation, the moon-forming debris that impact should have produced is missing. Where did it go? What happened to it? There is no satisfying answer. One can argue that the debris was somehow reaccreted into the planet quickly, but the orbital mechanics of debris reaccretion don't generally produce that outcome cleanly. One can argue that the impact happened very early, before Venus had fully formed, and that the subsequent accretion of remaining disk material absorbed the debris. But that creates different problems, namely that the post-impact accretion would have tended to respin Venus in the prograde direction as it swept up material still moving in the original disk rotation direction. By the 1970s and 80s, as simulations of planetary formation and impact physics became more sophisticated, the simple late impact hypothesis was in serious trouble. Not dead, because nothing in planetary science dies entirely without something better replacing it, but the enthusiasm had visibly waned. The energy budget didn't quite work. The moon problem was uncomfortable. The lack of surface evidence, while explainable by invoking later volcanic resurfacing, required a chain of assumptions that started to feel circular. The community kept the hypothesis on life support and started looking for alternatives. Around the year 2008, something interesting happened in the planetary science literature. The impact hypothesis, which had been quietly losing credibility for decades, came back. Not in its original form, but revised, smarter, repositioned in time in a way that addressed several of the original objections while opening new questions of its own. The original hypothesis had proposed a large impactor striking an already formed Venus late in the solar system's history, after the planet had finished accumulating its mass and settled into a stable spin. The new version shifted the event much earlier. It proposed not a single impactor striking a finished planet, but a merger between two large protoplanetary bodies during the accretion phase itself, while Venus was still in the process of becoming Venus. The distinction sounds subtle. It is not subtle. It changes almost everything about how the hypothesis works physically. In the original picture, Venus begins its life spinning prograde, like every other inner planet, and then something comes along and violently reverses that existing spin. That means you need to extract all the angular momentum Venus has already built up in the prograde direction before you can start building retrograde angular momentum in its place. Two enormous steps, both requiring catastrophic energy. In a merger picture, two Mars-sized protoplanetary bodies collide and stick together while Venus is still forming. The combined object that results inherits the angular momentum from both collision partners. If the geometry of that collision, the approach angles, the relative velocities, the mass distribution, produces a net retrograde angular momentum in the merged body, then the resulting proto-Venus is simply born rotating backward. There was never a prograde spin to reverse. The spin was set at the moment of birth by the collision geometry, not overwritten afterward. This is a meaningfully different story, and it is a story that fits much more naturally into what we actually know about how terrestrial planets form. The formation of rocky planets was not an orderly, sequential, predictable process. It was chaotic. The protoplanetary disk contained enormous numbers of Mars-sized and larger bodies wandering through intersecting orbits, colliding, merging, breaking apart, and recombining. The formation of Earth itself culminated in the well-documented giant impact that produced the Moon, a collision between proto-Earth and a Mars-sized body called Theia. That event was not unusual for the era. It was one of many large collisions happening throughout the inner solar system during the first 100 million years or so of the solar system's history. In this context, a merger between two large bodies that produced the retrograde spinning proto-Venus is not a remarkable event. It is the kind of thing that was happening constantly. The probability that any given merger geometry would produce retrograde rotation is low, maybe a few percent. But we're not trying to explain why every planet rotates backward. We're trying to explain one planet, one low probability outcome, happening once in a solar system full of active collisions is entirely acceptable. The merger hypothesis also handles the Moon problem more gracefully than the late impact hypothesis. When planets are still in the accretion phase, the debris generated by collisions tends to be rapidly reaccreted into the growing planet rather than settling into stable long-term orbits. The planet is still sweeping up surrounding material. Anything that gets ejected is likely to fall back and before it can coalesce into a stable moon. The Moon formed around Earth because the Theia impact happened late enough and in just the right geometry that a stable debris disk could persist long enough to coalesce. If Venus's defining merger happened somewhat earlier, or in a different geometry, the debris would have been reabsorbed rather than left in orbit. The result is a planet with no moon, which is exactly what we observe. There are still problems. There are always problems. You need two bodies of approximately the right size to be in the right place at the right time, approaching each other at the right angle. Each of these requirements is physically reasonable, but they have to all be true simultaneously, and the probability of that specific combination is not high. More importantly, the hypothesis is not directly testable. The merger, if it happened 4.5 billion years ago, and every piece of evidence from that era has been buried under billions of years of subsequent geological activity. We cannot look at Venus today and find a smoking gun that says two bodies merged here at this time, in this configuration. Still, the merger hypothesis is taken seriously. It is consistent with the known physics of planetary accretion. It does not require special post-formation physics. It naturally explains both the retrograde rotation and the absence of moons. It is a respectable candidate, sitting alongside the slow physics explanations as one of the main frameworks planetary scientists currently consider. But to understand why the slow physics explanations have gained so much ground, we need to go deeper into what forces are actually acting on Venus right now, and have been acting on it continuously for 4.5 billion years. In the early years of the 21st century, two planetary dynamicists named Alexander Correa and Jacques Lasker published a series of papers that changed how many researchers think about the Venus rotation problem. Their central argument was that you do not need a catastrophic event to explain Venus's current spin. You need time, a thick atmosphere, and 3 continuously operating torques, none of which is individually dramatic, but all of which are patient in the way that only cosmic timescales allow. Their framework, now often called the Correa-Lasker model, begins with a simple but important point. A planet's rotational state is not frozen at formation. It is a dynamic variable that evolves over time under the influence of every force acting on it. If those forces are small but persistent, and if the planet has enough time, the rotation can drift very far from its initial condition. Given 4.5 billion years, even tiny torques can accumulate into transformative changes. For Venus, Correa and Lasker identified 3 main torques that have been acting on the planet's rotation continuously throughout its history. The first is the solar gravitational tide. The sun's gravity does not pull equally on all parts of Venus. It pulls slightly harder on the near side than on the far side, because gravity weakens with distance. This differential pull stretches Venus slightly into an elongated shape, creating small tidal bulges on the side facing the sun and the side facing away. If Venus were not rotating, these bulges would align perfectly with the sun. But Venus is rotating, and the material of the planet takes time to deform and respond to the tidal stress. Because of this lag, the bulges are slightly offset from the Sun-Venus line. The near side bulge is dragged slightly ahead in the direction of rotation. The far side bulge lags slightly behind. The sun's gravity pulls on these offset bulges, and because they are misaligned, the net gravitational pull has a rotational component. It exerts a torque. The direction of this torque always opposes the rotation. If Venus is spinning prograde, the torque acts to slow it down. If Venus is spinning retrograde, the torque acts to slow that down too, which means it is pushing in the prograde direction. The gravitational tide is fundamentally a braking mechanism. Over long enough timescales, it would tend to pull any rocky planet in a synchronous rotation with the sun, one face permanently locked toward the star, the same way the moon is permanently locked toward Earth. Left alone, this is where Venus would eventually end up. One face, broiling forever in permanent noon. The other face, frozen in perpetual night. But the gravitational tide is not alone. The second torque is the atmospheric thermal tide, and this is where Venus's extraordinary atmosphere becomes central to the story. The sun heats the day side of Venus. The heated gas expands and rises, creating a low-pressure region near the surface and a corresponding high-pressure region higher in the atmosphere on the day side. The night side is cooler, denser, and heavier. This creates a thermal asymmetry, a density distribution that is not symmetric about the Sun-Venus line. Because the atmosphere is rotating, and because the thermal response of the atmosphere lags behind the heating pattern, the actual density distribution ends up offset. There is a slight phase difference between where the sun is overhead and where the atmospheric density bulge is located. This offset atmospheric mass exerts a gravitational pull on the solid planet below it, just as the planet exerts a gravitational pull on the atmosphere. And because of the offset, this pull has a rotational component. It exerts a torque. Here is the crucial point. The thermal tide torque acts in the opposite direction from the gravitational tide torque. Where the gravitational tide always breaks the rotation towards synchronous lock, the thermal tide pushes against synchronous lock. It pushes the rotation toward faster, more extreme states. On Venus, with its enormously massive atmosphere, the thermal tide torque is strong enough to matter. It does not simply nudge the rotation. It actively competes with the gravitational tide for control of the planet's spin state. The third torque is core mantle friction. Venus has a differentiated interior, a dense iron core, at least partially liquid, surrounded by a rocky silicate mantle. These two layers can rotate at slightly different rates. When the external tidal torques act on the planet, they act primarily on the mantle, the rocky outer shell. The core, insulated from direct tidal forcing, does not immediately follow. There's friction at the boundary between the core and the mantle, the core-mantle boundary, and that friction transfers angular momentum between the two layers. This is a smaller effect than the tides, but it is not negligible over billions of years, and it acts as a damping mechanism, affecting the speed at which the rotation responds to the tidal forcing. When Correa and Lasker assembled these three torques into a coupled dynamical system and ran numerical simulations starting Venus from a wide range of initial rotational states, they found something remarkable. The system did not converge to a single outcome. It had multiple possible stable states, what dynamicists call attractors, that the rotation could settle into depending on initial conditions and the precise values of the various parameters. Some attractors corresponded to prograde rotation. Some corresponded to retrograde. Some corresponded to very slow rotation near zero. And crucially, the current observed state of Venus, slow retrograde rotation with a high axial tilt, was consistent with one or more of those attractors. This means that the current state of Venus can be explained without any catastrophic event. Given the right initial conditions, which need not be particularly special, and given 4.5 billion years of continuous action by these three torques, the rotation evolves naturally toward the current state. No impact required, no merger required, just physics, patience, and an unusually thick atmosphere. This is a profound shift in how to think about the problem. The impact and merger hypotheses say something unusual happened to Venus, and we're trying to identify what. The Correa-Lasker framework says nothing unusual needed to happen. Venus is doing what the physics inevitably leads to under the conditions that exist in the solar system. The current state is not the result of an anomaly. It is the result of ordinary forces operating over extraordinary timescales. One of the more unsettling results buried inside the Correa-Lasker analysis is this. Even within the slow physics framework, there are at least two completely different evolutionary pathways that both lead to exactly the current state of Venus. And those two pathways are observationally indistinguishable from the outside. The first pathway is what you might call genuine rotational reversal. Venus begins its history rotating prograde, at some speed broadly similar to early Earth. Over billions of years, the combined effect of the gravitational tide, the thermal tide, and core mantle friction gradually drains the prograde angular momentum. The rotation slows. It slows further. At some point, it passes through zero, and then, pushed by the thermal tide, which is now reinforcing the retrograde motion, it begins to build up speed in the retrograde direction, until it reaches the current value of 243 days, where the gravitational and thermal tides are approximately in balance. Throughout this entire process, the axial tilt of Venus remains roughly as it started. The planet is always right side up in the sense that its spin axis points in roughly the same direction it always has. The direction of spin has reversed, but the orientation of the axis has not fundamentally changed. The second pathway is what you might call axial flip. Venus again begins rotating prograde, but instead of the rotation itself slowing and reversing, the rotation axis becomes dynamically unstable under the combined torques. The axis begins to precess and migrate. It drifts away from its original orientation, tilting further and further from the solar system's reference plane. Eventually, it tilts past 90 degrees. It keeps going, driven by the torque dynamics, until it reaches approximately 177 degrees, essentially pointing the other way. The planet is now upside down by the convention we use to define planetary orientations. At this point, even though the planet in its own reference frame may still be rotating in roughly the same direction it always has, from our external perspective it now appears to be rotating retrograde. The flip of the axis has produced retrograde motion without requiring the rotation itself to actually reverse direction. Both pathways end at the same place. Slow retrograde rotation, high axial tilt, 243-day period. Everything that we currently observe about Venus is consistent with either evolutionary history. The internal structure, the atmospheric composition, the gravity field, the surface features, none of these distinguish between a planet that reversed its spin and a planet that flipped its axis. This is called observational degeneracy. Multiple histories collapse into the same present, and the present alone cannot tell you which history was real. For Venus, observational degeneracy is a fundamental obstacle. We do not have preserved ancient crust that might encode information about the planet's early orientation. We do not have a moon whose orbital evolution would have been shaped by the rotation history and could now serve as a record. We do not have a magnetic field preserved in ancient rocks that might show us how the rotation axis was oriented at different times in the past. We have the current state, and the current state is consistent with too many histories. When you combine this with the impact and merger hypotheses, the degeneracy becomes even deeper. You now have at least 4 distinct possible histories for Venus's rotation: gradual spin reversal, axial flip, early merger with retrograde geometry, and late catastrophic impact, all of which produce the current observed state. Distinguishing between them requires evidence that has been largely or entirely erased from the geological record. This is not a failure of science. It is a genuine epistemic limitation imposed by the nature of the planet itself. Venus has been an exceptionally thorough destroyer of its own history, and that destruction is what makes this problem so difficult and so enduring. To understand why we cannot resolve this question with current data, you need to understand what kind of planet Venus is, geologically speaking, which is to say, you need to understand how comprehensively Venus has wiped its own past. On Earth, we can read deep geological history. The oldest mineral grains ever found on Earth, zircon crystals from Western Australia, date to approximately 4.4 billion years ago, nearly as old as the planet itself. Through these preserved remnants, and through the continuous geological record written in rocks and sediments, we can reconstruct Earth's history in considerable detail, going back most of the way to formation. We have plate tectonics, which continuously cycles old crust down into the mantle and creates fresh crust at spreading ridges. But even so, enough ancient material is preserved at the surface to anchor our understanding of the deep past. Mars has preserved surface features from its first billion years. Ancient crater basins, dried riverbeds, layered sedimentary deposits that tell us about the climate of early Mars when the planet was warmer and wetter than it is today. The geological record is incomplete and disrupted, but it exists. You can read it. The Moon has its heavily cratered highland regions, ancient terrain that has been sitting essentially undisturbed since the era of heavy bombardment 4 billion years ago. That cratered surface is a historical record in the most literal sense. Every impact that occurred during the solar system's violent early history left a mark, and most of those marks are still there. The Moon is a planetary fossil, preserving the conditions of the early solar system in its topography. Mercury has its enormous calorous basin, its global contraction fractures, its ancient surface largely preserved because Mercury has no atmosphere capable of driving significant erosion, and no active volcanism reshaping the surface in the current era. Venus has none of this. The surface of Venus is young. The best current estimates, based on crater density analysis and volcanic feature analysis, put the average surface age at somewhere between 500 million and 1 billion years. In geological terms, this is recent. The surface we see in our radar images from the Magellan mission in the 1990s represents a world that has been recently and comprehensively resurfaced by volcanic activity. Whatever lay beneath, whatever ancient terrain encoded the record of Venus's early history, has been buried under lava flows and tectonic deformation. There is ongoing debate about whether this resurfacing happened all at once in a single catastrophic volcanic event, a kind of global thermal purge, or whether it has been occurring continuously. But regardless of the mechanism, the result is the same. The geological record of Venus's first 3.5 billion years is gone. If rotation-sensitive features once existed in the ancient crust, features that might tell us how the planet was oriented, how fast it was spinning, whether the spin axis was stable or migrating. They have been overwritten. Venus also has no moons. This point deserves more attention than it usually receives in popular accounts of the Venus problem. A moon is not just a picturesque companion. It is a dynamical witness. Earth's moon has been orbiting in a specific plane, at a specific distance, in a specific direction, for most of Earth's history. By modeling how the moon's orbit has evolved under Earth's gravitational and tidal influence, we can work backward and infer things about Earth's rotation history. The moon is a record that has been continuously updated with information about Earth's spin, and it is a record we can partially decode. Mars's moons, tiny as they are, play a similar role. Phobos is spiraling inward toward Mars, and the rate of that spiral tells us about the tidal dissipation happening inside Mars, which tells us about its interior structure, which connects to its rotational evolution. Even this small amount of information is valuable. Venus has no such witness. Whatever happened to its spin has been witnessed by nothing that survived to tell us about it. And Venus has no global magnetic field. The absence of a magnetic field means there is no ongoing recording of the planet's rotational orientation in its interior. On Earth and Mars, ancient magnetic field directions preserved in rocks that cooled and solidified long ago act as a geological compass, pointing toward wherever the magnetic pole was at the time of formation. By reading these paleomagnetic signatures in sequence, geologists can reconstruct how the rotation axis has moved over geological time. Venus denies us this tool entirely. Even if it had an ancient magnetic field, the resurfacing has erased whatever rock record might have preserved it. What remains is the atmosphere, and specifically the isotopic composition of the atmospheric gases. This is one of the few places where Venus's ancient history has left a legible, if faint, chemical signature. There is a measurement buried in Venus's atmospheric chemistry that hints at a different past, and it connects the rotation mystery to a question that has been gaining serious scientific attention in recent years. Was Venus ever habitable? The measurement involves deuterium. Deuterium is a heavier isotope of hydrogen. Regular hydrogen has a nucleus consisting of a single proton. Deuterium has a nucleus with one proton and one neutron, making it roughly twice the mass of ordinary hydrogen. Chemically, deuterium behaves almost identically to regular hydrogen. But the difference in mass matters enormously when it comes to atmospheric escape. When a planet loses hydrogen to space, it loses it through a process driven by solar radiation splitting water molecules in the upper atmosphere. The hydrogen atoms, freed from the water molecules, can escape the planet's gravity if they are moving fast enough. The lighter, ordinary hydrogen atoms escape more readily. The heavier deuterium atoms are less likely to have escape velocity and more likely to remain. Over time, as a planet loses hydrogen, its remaining atmospheric hydrogen becomes progressively enriched in deuterium. The ratio of deuterium to ordinary hydrogen rises as the planet loses water. Earth's atmosphere has a deuterium to hydrogen ratio of roughly 1.5 times 10 to the negative 4. This is close to the primordial solar system average, consistent with a planet that formed with water and has not lost catastrophically large amounts of it over its history. Venus's atmosphere has a deuterium to hydrogen ratio approximately 150 times higher than Earth's. 150 times. This is an enormous enrichment, and its interpretation is relatively straightforward. Venus has lost a staggering amount of hydrogen to space over its history. The most natural source of that hydrogen is water. Venus started with water, probably a great deal of it, and most of that water has been lost. What remains is a chemical residue of destruction, the heavy isotope left behind like sediment after the lighter component has evaporated away. Estimates of how much water Venus originally held vary, but some calculations suggest that if the original water inventory is reconstructed from the current deuterium enrichment, Venus might have had enough water to cover its entire surface to a depth of several hundred meters. That is comparable to Earth's oceans. It is enough water to have supported a climate radically different from the hellscape Venus presents today. It is potentially enough water to have supported life? This is the Venus habitability question, and it has attracted intense interest in the past decade. Models of early Venus suggest that the planet may have maintained a temperate climate with liquid water oceans for perhaps 2 billion years or longer, depending on the rate at which the young sun was brightening. At some point, the increasing solar output tipped Venus's climate into a runaway greenhouse state. Water evaporated into the atmosphere. Water vapor is a powerful greenhouse gas, so more warming resulted, which evaporated more water, which produced more warming. The ocean boiled. The water vapor was split by solar radiation in the upper atmosphere. The hydrogen escaped to space. The oxygen remained, bound into rocks and the suffocating carbon dioxide atmosphere that remains today. But here is the connection to our central question. The timing and speed of Venus's water loss is linked to its rotation. A Venus rotating more quickly would have generated different atmospheric circulation patterns, different climate dynamics, a different response to the increasing solar output. A Venus with a very slow retrograde rotation, like the one we see today, has a very different climate structure than a fast-rotating Venus would have. If the rotation had already slowed significantly before the runaway greenhouse began, that slow rotation may have contributed to the climate's instability. Alternatively, if Venus suffered a major impact or merger early in its history that both reversed its spin and blew off a large fraction of its original atmosphere and water, then the water loss and the spin reversal are part of the same story. The same catastrophe that flipped the planet may have also vaporized the oceans and initiated the long process of atmospheric escape that left behind the deuterium signature we measure today. These are not cleanly separable scenarios. The spin history and the water history and the atmospheric history are all woven together, each one influencing and depending on the others. You cannot fully reconstruct any one of them without reconstructing all three simultaneously, and we do not currently have the data to do that. When the mainstream explanations for a problem have all run into serious obstacles, the scientific community begins to explore the edges, not recklessly, not irresponsibly, but with the honest acknowledgement that if the obvious answers don't work, perhaps something less obvious is required. The Venus rotation problem has been generating edge hypotheses for decades, and some of them are worth understanding because they illuminate dimensions of the problem that the mainstream models tend to underemphasize. Consider the possibility of a missing planet. The inner solar system today has 4 planets: Mercury, Venus, Earth, and Mars. But this configuration is not necessarily the original one, and modern planetary formation simulations have consistently suggested that the early solar system was more crowded and more chaotic than its current state implies. Some simulations produce scenarios in which one or more terrestrial planets formed early, but were subsequently lost, ejected by gravitational interactions with the giant planets during a period of orbital instability, or destroyed in collisions with surviving bodies. The hypothesis of a lost inner planet, sometimes labeled Planet V in the literature, proposes that a 5th terrestrial body existed in the early solar system and played a role in shaping the evolution of the inner planets before being removed. If such a body existed in an orbit that brought it into close proximity with Venus at some point, the gravitational interaction could have torqued Venus's spin axis, contributing to or initiating the departure from normal behavior. Multiple close encounters during a chaotic orbital phase could have been more influential still. This hypothesis has no direct evidence. It is inferred from the difficulty of reproducing the current inner solar system configuration from purely the 4 surviving planets. Some simulations do better when they include an additional body that is subsequently removed, but the argument is indirect, model-dependent, and not universally accepted. The reason it persists is that it opens a conceptual door. Venus's unusual rotation might not be about Venus at all. It might be a record of interactions with a body that no longer exists and cannot be directly studied. The rotation is a frozen record of an encounter with a vanished neighbor, and we're trying to read that record without being able to examine the other party. There is also the hypothesis of close gravitational encounters between early Earth and early Venus. In the chaotic first 100 million years of the solar system's history, the orbits of the inner planets were less stable and less well separated than they are today. Models of early solar system evolution sometimes produce episodes in which Earth and Venus had close approaches to each other, not impacts, but near misses close enough for significant gravitational interaction. During such approaches, angular momentum can be exchanged between the two bodies. The outcome depends on the geometry, but in some configurations, Earth would end up spinning faster in the prograde direction, while Venus would end up with its angular momentum partly depleted or redirected. This scenario has a certain appeal because it could explain multiple things simultaneously. The similarity between Earth and Venus in composition and mass comes from their common formation region. The difference in rotation comes from their early interactions. The hypothesis remains a minority view because it is hard to verify and because simulations can produce the observed outcomes without invoking it. But it illustrates again the key insight that Venus cannot be understood in isolation. It is a planet embedded in a solar system, and the solar system, during its early history, was a place where planets influenced each other in ways we are still trying to fully reconstruct. At the most exotic end of the spectrum is the capture hypothesis. Venus did not form where it currently orbits. It formed elsewhere in the solar system, perhaps in the outer regions, and was somehow captured into its current orbit later, bringing its own independently derived rotational history with it. This would naturally explain the retrograde rotation, since a body forming in a different part of the solar system would not necessarily inherit the same rotational direction as the inner disk. The problem is Venus's composition. The silicate and iron content of Venus is entirely consistent with an inner solar system origin, with formation at approximately the current distance from the Sun. A body forming in the outer solar system would be expected to have a very different compositional signature, enriched in volatiles, water, methane, ammonia, and other compounds that condense at lower temperatures. Venus shows none of this. Its composition argues strongly against an outer system origin. The capture hypothesis remains on the shelf because the most direct available evidence contradicts it. These exotic hypotheses matter not because any of them is likely to be correct, but because they reveal the true scope of the problem. Venus's rotation cannot be fully understood by looking at Venus alone. It is a consequence of the entire history of the solar system, including bodies that no longer exist, interactions that left no direct record, and processes that are themselves only partially understood. Let me return one final time to the atmosphere, because there is a specific feature of it that sits inside every slow physics model of Venus's rotation and has never been fully explained. And the failure to explain it is not a minor gap. It sits near the heart of the problem. The superrotation of Venus's upper atmosphere, where clouds at 65 kilometers altitude race around the planet approximately 60 times faster than the surface beneath them, has been known since the 1960s. It was confirmed and refined by subsequent missions, most recently by the Japanese Akatsuki spacecraft that has been orbiting Venus since 2015 and returned remarkably detailed observations of atmospheric dynamics. Superrotation exists. It is real. Its magnitude is well measured. What is not fully understood is why it is so strong. The proposed mechanism involves atmospheric waves, specifically Kelvin waves and Rossby waves, which are large-scale oscillations in the atmospheric flow that propagate both horizontally and vertically. The argument is that these waves preferentially transport angular momentum upward through the atmosphere, continuously injecting it into the upper cloud layers and maintaining the superrotation against the friction that would otherwise slow it down. This is a plausible mechanism, and it is supported by some of the observational data from Akatsuki. But the models that implement this mechanism do not yet fully reproduce the observed superrotation in all its details. The Akatsuki data has revealed unexpected features: large stationary wave structures that appear locked to the surface topography below, asymmetries between the northern and southern hemispheres, variations in wind speed with latitude and altitude that don't fit cleanly into the theoretical picture. The atmosphere of Venus is more complex than the models capture. This matters directly for the rotation problem because the thermal tide that plays such a central role in the Korea-Alaska framework depends on the atmospheric dynamics we are discussing. The strength and phase of the thermal tide depends on how the atmosphere moves, how it distributes heat, how waves propagate within it. If our model of the atmospheric dynamics is incomplete, and the Akatsuki data suggests it is, then our model of the torque the atmosphere exerts on the solid planet is also incomplete. The slow physics framework is built on the assumption that we understand the atmospheric coupling well enough to model it. The observations from Akatsuki suggest that assumption needs revision. The coupling is more complicated than the models currently capture. And if the coupling is more complicated, then the long-term rotational evolution driven by that coupling may be different from what the models predict. This is the deepest layer of the problem. We do not just have multiple possible histories for Venus that we cannot distinguish. We also have an incomplete understanding of the current state of the planet, specifically of the atmospheric dynamics that drive some of our leading explanations. The uncertainties compound. The farther back in time we try to reconstruct, the more those compounding uncertainties grow. Venus is a problem at the edge of what current planetary science can confidently address. The situation is not static. The period of observational scarcity that has characterized Venus science for the past several decades is coming to an end. A coordinated fleet of new missions is currently in development, aimed at Venus with more sophisticated instruments than have ever been deployed there before, and the data they return will change our picture of the planet significantly. NASA's Da Vinci mission, which stands for Deep Atmosphere Venus Investigation of Noble Gases, Chemistry, and Imaging, is designed around a descent probe that will enter Venus's atmosphere and fall through it from the top to the surface, sampling and analyzing the atmospheric composition at every altitude along the way. The scientific priority is the isotopic composition of the atmospheric gases, particularly the deuterium to hydrogen ratio, and the abundances of noble gases like xenon, neon, and argon. These measurements are sensitive to the history of atmospheric evolution in ways that current data, mostly derived from early Soviet-era missions in the 1970s and 80s with the limited instrumental precision of that era, cannot resolve. By measuring these isotope ratios with modern instrument precision, Da Vinci can distinguish between different histories of atmospheric loss. A Venus that lost its water rapidly and early, perhaps in connection with a major impact or during the initial runaway greenhouse transition, should have a different isotopic signature than a Venus that lost its water gradually over billions of years through steady thermal escape. The signatures are not perfectly clean, but they are distinguishable with sufficient precision. This matters for the rotation problem because the atmospheric history and the rotation history are coupled. A rapid early atmospheric loss event connected to a catastrophic impact would suggest the impact hypothesis gets observational support. A gradual loss profile consistent with steady-state thermal escape would favor the slow physics picture in which no single catastrophic event is required. Da Vinci will not definitively resolve the spin mystery, but it will constrain the set of viable histories in a way that current data cannot. NASA's Veritas mission, Venus emissivity, radio science, NSAR, topography, and spectroscopy, is an orbital mapping mission designed to produce the most detailed picture of Venus's surface and interior structure ever obtained. Where Da Vinci samples the atmosphere, Veritas charts the planet beneath it. The gravity field measurements Veritas will perform are particularly relevant to the rotation problem. The distribution of mass inside Venus determines how the planet responds to tidal forcing, which is a central parameter in the slow physics rotational evolution models. Better gravity data means better constrained tidal response, which means better constrained models of how the rotation has evolved over billions of years. This does not uniquely solve the problem, but it narrows the uncertainty in the models. The European Space Agency's Envision mission will complement both NASA missions with its own suite of radar and spectroscopic instruments, providing additional topographic and compositional data from orbit. Together, these three missions will produce a step change in our understanding of Venus. The combination of detailed atmospheric chemistry, high-resolution surface mapping, and improved interior structure models will eliminate some hypotheses, strengthen others, and almost certainly raise questions that the current framework does not anticipate. That is how science progresses. Not with clean revelations, but with cycles of better data, generating better models, generating better questions. Whether the fundamental mystery of Venus's rotation will be resolved by the data from these missions is genuinely uncertain. Some of the information needed to distinguish between the viable hypotheses may be permanently unavailable, lost in the geological resurfacing that erased the ancient record. But the missions will narrow the space of possibilities significantly, and narrowing that space is itself a form of progress, even if it falls short of a definitive answer. We have been asking, throughout this entire investigation, what happened to Venus? But there is a more fundamental question that the Venus rotation problem forces us to confront, a question about the nature of knowledge itself, about what it means to reconstruct the past from a present that has been heavily edited. Venus is an object lesson in what philosophers of science call underdetermination. The current state of Venus is consistent with multiple different histories. The observations underdetermine the theory. No amount of additional observation of the current state of Venus will uniquely resolve which history was real, because too much of the physical record that would distinguish between them has been destroyed. The geological history is buried. The ancient magnetic record is absent. The moon that would have encoded the dynamical history was never formed or has been gone for billions of years. We are left with a present that is consistent with too many pasts. This is not unique to Venus. It is a general feature of how knowledge about the deep past works. The universe does not retain perfect records of everything that has happened. Physical processes destroy information. Entropy erases the specific in favor of the general. The more time passes, the more the details of what happened are replaced by the statistics of what could have happened. For Venus specifically, this means something humbling. We live 93 million miles from this planet. We have sent spacecraft to it. We have mapped its surface with radar. We have deployed probes that survived long enough in its crushing, scorching atmosphere to return data. We have devoted the careers of serious scientists to understanding it for 60 years. And we still do not know why it spins the way it does. This is not failure. The effort has produced real, substantial, important understanding. We know the mechanisms that could drive the rotation. We know the constraints each hypothesis must satisfy. We know what evidence would be needed to resolve the question, and we know that much of that evidence is no longer available. Understanding the shape of your ignorance is itself a form of knowledge. Science at its best makes ignorance precise. But there's a philosophical dimension here that extends beyond Venus. We are currently discovering planets around other stars by the thousands. The catalogs grow every year. For the vast majority of these exoplanets, we have incomparably less information than we have for Venus. We see their shadows passing in front of their stars, or the tiny gravitational tug they exert on their star's motion. And from those minimal signals we infer sizes, masses, orbital periods, sometimes rough atmospheric compositions. From these clues we build models of what these planets might be like, what their histories might look like, whether they might harbor conditions friendly to life. Venus is a calibration point for that entire enterprise. If we cannot reconstruct the rotation history of a planet that is close enough to visit with spacecraft, whose surface we have mapped, whose atmosphere we have sampled, how confident should we be in our reconstructions of planets we can barely detect at all? The answer is not that we should give up. The answer is that we should be honest about what we know, what we don't know, and what may be in principle unknowable from the data available to us. Venus teaches us that the current state of a planet underdetermines its history, that the same present can arise from multiple different pasts, and that the physical record of what actually happened is often incomplete in ways that cannot be remedied by better instruments alone. We began with a disturbing fact. There's a planet next door, built from the same materials as our own world, sitting in the same neighborhood, formed from the same disk under the same physical laws, and it is spinning the wrong way. 60 years of physics have failed to fully explain it. Where does that leave us? The honest answer is in a state of informed uncertainty, which sounds like a consolation prize, but is actually the most accurate and therefore the most valuable place to be. We are not completely ignorant. We have a set of serious, physically grounded hypotheses. Early merger, late impact, gradual tidal reversal, axial flip, all of them viable, all of them incomplete, none of them proven. We have identified the mechanisms that could drive each outcome. We have mapped the evidence that would distinguish between them, and we have established that most of that evidence no longer exists. We know that spin is a fossil. It encodes the moment of a planet's birth, the angular momentum accumulated through every collision that built the growing body from dust to world. We know that Venus's fossil has been overwritten. Something rewrote it so thoroughly that the original cannot be read, and the rewriting itself may have happened through multiple different processes that all left the same present-day signature. We know that Venus's atmosphere is not a passive shroud, but an active engine, working continuously on the planet's rotation through thermal tides and surface friction and momentum exchange, and that this engine has been operating in some form for 4.5 billion years. We know that the atmosphere we see today is not the atmosphere that was operating during Venus's early history, and that the evolution of the atmosphere and the evolution of the rotation are inextricably linked. We know that the solar system Venus grew up in was far more violent and chaotic than the orderly diagram in any textbook suggests. Planets formed, collided, merged, and in some cases were lost entirely. The stable configuration we inhabit today is the quiet aftermath of an extremely turbulent process, and the properties of the surviving planets, including their rotations, reflect that turbulence in ways we are still working to decode. And we know that Venus is not going to confess. It has buried its secrets under layers of lava, sealed them under a crushing, acidic atmosphere, disposed of the witnesses by never forming or retaining any moons, and erased the magnetic diary that might have recorded its rotational biography. Whatever happened 4.5 billion years ago is mostly gone. What remains is a planet spinning patiently in the wrong direction, telling us in the only language physics allows that something significant occurred, while declining to specify what. There's a final thought that this investigation leads to, one that goes beyond Venus and beyond planetary science, into something that feels almost like the kind of reckoning that arrives at the end of long, honest inquiry. The universe is full of objects whose current states are legible, whose properties can be measured, cataloged, analyzed. But the universe is also full of erased histories, events that happened and left consequences but destroyed their own evidence, processes that shape the present but are no longer accessible from it. Every time we look at a distant world and confidently narrate how it came to be, we should carry with us the lesson of Venus. That confidence is earned only when the evidence is genuinely sufficient. And the evidence is not always sufficient. The past has a way of hiding itself, of covering its tracks, of rewriting its own record with the very processes that followed it. Geology buries geology. Volcanism buries volcanism. Time buries time. Venus is sitting 93 million miles away from us, the closest major planet in the solar system. The world we knew least well for longest, the planet that resembles us most closely and behaves most differently. It is spinning at walking speed in the wrong direction, with a day longer than its year and an axis that points almost directly opposite to where it should. It has been doing this since before life existed on Earth, since before the ocean stabilized, since before the first cells learned to divide and copy and persist. It will still be doing it when the next generation of missions arrives. Da Vinci coming down through that dense, poisonous sky, measuring the chemical residues of ancient oceans. Veritas mapping the gravity field that encodes the interior's response to 4.5 billion years of tidal forcing. Envision painting the surface in radar wavelengths, looking for the subtle signs of ongoing volcanism. Try to read a geological record that may already be too young to tell us what we need. They will find things we do not currently know. They will answer some questions. They will raise new ones. The space of viable histories for Venus's rotation will narrow, and the narrowing is worth the effort and the cost, even if the final resolution remains beyond reach. Because Venus has already given us something valuable, something beyond the facts of its rotation period and axial tilt and atmospheric mass. It has given us a demonstration of the limits of reconstruction, a proof that the past is not always recoverable, a clear-eyed reminder that the universe is under no obligation to preserve the evidence we need to understand it. Science does not promise answers to every question. It promises a method, a way of asking questions rigorously and following the evidence honestly and acknowledging what the evidence does and does not support. On Venus, the evidence runs out before the question is answered, and that is worth knowing. That is itself a result. The planet next door is spinning the wrong way. We have spent 60 years trying to understand why. We know more now than we did. We know the shape of what we don't know, which is a different and harder kind of understanding. The missions are coming. The data will follow. And somewhere in that data may be the thread that finally begins to unravel the story. Or perhaps not. Perhaps Venus will remain the solar system's most eloquent unanswered question, a retrograde monument to the limits of knowledge, turning slowly against the current of all expectation, patient and silent and finally, beautifully, irreducible.